Good afternoon. I'm Victor Darnay, Professor of Mathematics at Bryn Mawr College and also Director of the Environmental Studies program there. I'm going to talk to you today about how to use issues of civic engagement in mathematics courses, although I think what I'll talk about is also relevant to science courses. And my goal is to show a range of different types of ways you can use civic engagement, from very simple ones that don't take much effort all the way to very sophisticated and complicated approaches using service learning. I know people are kind of at a range of comfort levels in using issues of civic engagement, and I want to show how at different levels of engagement there are ways to include civic engagement in mathematics. So to get started, I'd like you to jot down your name, your institution, and then what course or courses are you already teaching or might you teach that would include issues of civic engagement. So you can pause while you do this little bit of homework. My next question for you are, what are some issues facing the world and the nation that you are concerned about? I'll do that again. What are some issues facing the nation and the world that you are concerned about? Take a minute or two to do a quick write, and again, pause the video while you're doing that. Now, as a way of introducing yourself to the other people in the webinar, I'd like you to go around and each person introduce themselves, say your name, what discipline you teach in, what course you're thinking about using for a sensor type course, and then say one issue that you're concerned about. Again, we'll pause while you all do that. And you might share the list of topics you've come up with. Here, I'll re-say that. So in the workshop at this stage, I had participants share out with the whole group some of the issues they were concerned about, and we made a list of some of those concerns. So the goal of our webinar is to show how the math that we learn is connected to these issues that you care about. And this question of issues facing the nation and the world that you are concerned about, this is how I start all of my math classes now, to get the students thinking about what they care about and challenge our math class over the next semester to make connections between the math we learn and these issues the students are concerned about. And a reason I do this is the issue of student motivation, that so often we hear students say, what is math good for? And here, right from the get-go, I'm letting them know that part of our goal in the class is to see what math is good for. And it's good for many things, and in particular, it's good for things that they care about. And I came up with this idea as a way to launch my math classes by reading the book, What the Best College Teachers Do by Ken Bain. And in there, he has a very interesting example of faculty members teaching anatomy. And one of the faculty members he refers to says to the class, well, this semester we're going to learn about human anatomy. I'm sorry to say it's kind of dull and boring. There's a lot to memorize, a lot of complicated words you're going to need to learn how to pronounce and how to write, and a lot of connections of all these pieces of the body. And I'll do the best I can to try to make it interesting, but we're pretty much just going to have to slog through it. And then he talks about a second professor of anatomy who says, several years from now, you're probably going to be a medical physician. You may be working in an emergency room. A patient is wheeled in on a gurney suffering from severe injuries. You will have 2 minutes to figure out what their injuries are and start treating them, or they die. That is what this course is about. Which of those two approaches would you find more exciting and get you more eager to learn? I think most of us would agree it's the second one, where the professor has painted a compelling picture of the purpose of the course and how it links into a larger goal that many of the students have. So I'll start again. This question of student motivation and how do we get students to be motivated, I think is a general theme behind all the sensor approach of connecting math and science to issues of civic engagement. And from David Burns, I learned the following quote by William James from 1899. And I'll give you a minute to read this. So in summary, he says, any object not interesting in itself may become interesting through being associated with an object in which an interest already exists. So for many of our students, the object they're interested in is not mathematics. And if we can find some area they are interested in and show how it connects to mathematics, then they'll become more interested in the mathematics. A related quote, which I like, is the following: if you want to build a ship, don't drum up people to collect wood and don't assign them tasks and work, but rather teach them to long for the endless immensity of the sea. What I take away from this is the idea that humans naturally like to learn. The way we're designed as creatures is with curiosity and creativity and invention, and sometimes that's gotten us into trouble. But human history is amazing what the mind has been able to achieve over short periods of time. So people just naturally love to learn, and if we can tap into that natural curiosity and interest, then they'll do great things. Before I move on to examples of how I've incorporated civic engagement in my teaching, I want to lay a little bit of groundwork around brain-based research and what is the best practices and knowledge about how people learn, and what lessons does that give us for how we should teach. And here I'm referencing the book from the National Academy of Sciences called How People Learn: Brain, Mind, Experience in School. And one can get it free online. Connected with the webinar, I have a series of references and links, and so you can get the link to this book. They talk of 3 key principles of learning, and I'll actually start with what I call the 0th principle, which is to learn, people need to be interested and motivated. Their 3 key principles are the following, and for each one, you can take the time you need to read through them. I'll summarize these 3 key principles by kind of how I think of them. The first says that people bring pre-existing knowledge to a new situation, and sometimes that pre-existing knowledge includes misconceptions. And for the new knowledge to stick, one has to connect that new knowledge to old knowledge. The second key principle, and this is based on interviews with experts and asking them how they think about their knowledge, is that to remember factual knowledge, we need to organize that knowledge around key concepts. The key concepts are kind of the skeleton onto which we attach all the details that by themselves would be hard to know. But if students are to remember a lot of information, if they just try memorizing each of the individual facts, it's just too much to keep track of, and you don't know what's important and what's not important. So if we figure out what are the key concepts and remember those, then we can attach the different factual knowledge pieces to those key concepts. And third is the idea of metacognition, that if we give our students opportunities to think about their thinking, that will deepen their knowledge. So how these principles can apply to our teaching: if pre-existing knowledge is so important, how do we find out what our students' pre-existing knowledge is? And how do we help students link that pre-existing knowledge to the new material we're teaching them? What are the key concepts we are teaching in our course? If we as the instructor haven't gotten it clear in our own minds, then the students won't get it either. So helps us get organized by asking ourselves, what really are the key things we're trying to teach in this course? And then how can we connect the different parts of the course back to these key concepts? And then how do we determine if students have learned these key concepts? And finally, the metacognition, how are we going to give students opportunities in our courses to think about their thinking? And as we go through our webinar, we'll want to have you have opportunities to think about your thinking. All right, so let's start with the question, what are students interested in? If we try to tap into their interest to get them motivated to learn our courses. And one thing we can do is simply ask them what they're interested in. So that brings me to my first very simple civic engagement connection, which is in the standard homework problems we have in mathematics. Some of them claim to be connected to the real world and be applied problems. One that is very common in calculus is you have 100 feet of fence and you want to enclose the largest possible area. How do you do that? Well, this, in my mind, is a pretty dinky applied problem. It's not something we'd be so interested in real life. And so the assignment is just do 2 or 3 examples through the course of the semester. Take a homework problem that illustrates some mathematical concept, but then create an example of how that mathematics could be used in a more interesting real-world problem. So it's the same mathematics, but you kind of create the problem. And then I'll have students post these problems onto our course Blackboard, and I'll also have the students read a couple posts written by other students. So they get to learn from one another's ideas, and we begin to build some community in the class where we realize that our fellow classmates are excellent resources for our own learning. And I've done this type of assignment in Calculus 1 and 2. And here are 2 great examples that students generated, taking in real basic examples that you have in all calculus classes and showing how they apply to a much more interesting one. So this first problem is a related rate with water going into a tank. The water is going in at a certain rate, and we want to know how fast is the height of the water increasing. The application in the real world that the student came up with was, how fast is sea level rising if the ice in Greenland is melting at a rate of 195 cubic centimeters a year? Let me try that once more. How fast is sea level rising if the ice in Greenland is melting at a rate of 195 cubic meters a year? So this actually is one of the key issues facing the world right now. The student did this maybe 4 or 5 years ago, but already this issue of sea level rise is a key issue in the environment, and we see that it relates to this standard technique in calculus. The second example is, again, a very standard calculus problem, 2 airplanes flying past each other in different directions, and we ask how fast are they moving apart from one another. And the real-world application, I'll give you a moment to read it on your own. The student asks, at what rate is the vocabulary of the 2 children, one from a middle-class upbringing and one from a low-income household, how fast is the difference between vocabulary growth increasing in 3 years? So again, this idea of things moving at different rates apart from one another, and we're trying to find that out. And this was an example I would never have thought of, and it brings into play the students' interest in issues of social justice and inequalities in our society. The second type of assignment one can do is simply ask the students to find examples in the newspaper or on the web about mathematics, either mathematics in general or mathematics that has some connection to your particular class. And again, one can have them posted on a class website. They write maybe a 1-paragraph summary and also give the link to the article, and they read some of the posts of the other students and write comments about it. So here we're also showing students that writing is something you do in a math class. It's an important skill to have always, and so of course you're going to write in mathematics. The third example I'll give is a little more complicated than the first two, and it's a final project for a course. I did this project in my multivariable calculus course, and this project grew out of my own experience as a parent with my two boys in elementary school, in our neighborhood school, where the school used the Everyday Math program, which was developed by the University of Chicago. And in this Everyday Math program, the parents are given some handouts with suggestions on how to help support our students learning math by showing how math is connected to things in the everyday. For example, if you go shopping at the supermarket, have your children weigh things in the balances that you have in the grocery store. So the assignment is take some topic in the world in which you are interested and some topic from our course, in my case multivariable calculus, and show how they are connected. This assignment evolved. Initially I had a final project in multivariable calculus where I very carefully designed 4 projects that the student could choose, and I scaffolded step by step what they were supposed to do. And so I had a lot of control over what they were going to do, and they were kind of following the steps and the lead I had created. And this worked moderately well. For many students, doing some kind of project was new and innovative over what they typically would do in a math class. But the fact that I had set it out so much impacted their ability to be creative. And one of my colleagues, Rhonda Hughes, who's a brilliant educator, had done projects with her class, and I noticed that her assignment was simply having the students create their own project, whatever it was they were interested in. And initially I was a little nervous about taking this approach. I wasn't sure how the students would respond. Would they rise to the occasion and do something creative and thorough, or would they kind of goof off and not work very hard? Well, I was amazed by the fabulous projects that the students did once they were put in charge of creating their own project on what they were interested in. In these pictures, we see one team that produced a dance performance. In multivariable calculus, you have different coordinate systems, and in class, we kind of physically showed the meaning of polar and spherical coordinates, cylindrical coordinates, and so the students were doing a dance interpreting these different coordinate systems. A lot of students did projects about food and the shapes in food, and in multivariable calculus we learn about shapes and the math formulas generating these shapes. A fabulous project that was one of the best in the class was on Japanese architecture, and the students showed first the Japanese buildings and then recreated many of those same shapes using our math formulas and the computer graphics program Mathematica. So they really had to have a deep understanding of these formulas to be able to produce these shapes. Here you see kind of the party atmosphere. We linked the end of term poster session and project presentation to our end of semester department party. So first people came and had pizza, and then we looked at the posters and the presentations. People brought friends. On the top right, you see the college president who we had invited to show how exciting mathematics is. Another great project was jewelry, and the students recreated these jewelry shapes, again using the math formulas and Mathematica. On the left bottom, we have shapes that you would find in a dormitory room. There's one of a pillow, a blanket, other things you would find in a dormitory. And finally, on the bottom right, we have some of the elementary school students from my children's elementary school who came and showed their projects, which had to do with interesting shapes coming up in architecture, and my college students shared the projects back and forth. So one thing I learned from this project assignment was how creative and diligent students will be when they're working on something they really care about. And I kind of have to get out of the way with my own ideas and my own control and structure, and give them the freedom to take on these projects that they get really excited about. At my college, we interview seniors as they graduate to get their feedback on their college experience, and several students said that this assignment in multivariable calculus was one of the highlights of their 4 years of college. So these examples I've given are pretty general that one can do in any math course. Now I'd like to, and even in a science course really, focus more on math and sustainability, by which I mean environmental sustainability, which has become my interest over the past few years. Why sustainability? Well, one, it's an interdisciplinary topic, so there are lots of connections of math to the real world. It's certainly an authentic issue facing the world. It's really one of the great challenges of the 21st century, one of the greatest challenges ever facing humanity. And so what I'm going to do is give you examples of lessons that incorporate issues of sustainability to teach standard math material. And then I'll also talk about service learning projects that I've had my math students do that involve sustainability. At my college, we call service learning praxis. It's also called community-based learning. So a little review of what we mean by sustainability. There are various definitions, and people sometimes think it's all about the environment. But here, let's say sustainability is meeting the needs of present and future generations by reconciling economic growth, social development, and environmental protection. So certainly the environment is part of sustainability, but we also need economic prosperity, that people need to have jobs that provide a living wage. And in addition to the environment and the economy, we also need social conditions, that people need to be well treated through our society. So the challenge is how to combine these three issues in a way that supports society in the present and will also support it into the future. Okay, here I'm going to pause and backtrack back to this math and sustainability. People sometimes wonder when I mention that I'm interested in math and sustainability, how can math be connected to sustainability? They could imagine how biology and the environment and other sciences can have a link to sustainability, but they haven't thought much about how math can be connected to sustainability. So here I'm going to show that they're very natural connections, and indeed for some areas of sustainability it's hard to imagine how you could study it without using mathematics. So here I'll talk a bit about the course I teach on differential equations and modeling and how sustainability comes into that course. And I use a nice textbook by Blanchard, Devaney, and Hall, which takes a dynamical systems approach to the issue of differential equations. So it's very qualitative, and there's a lot of geometric visualization of the differential equations as compared to the more traditional analytic, where one's interested only in the formulas. And two examples I'll talk about that come up in this course are population growth and the notion of tipping points, which in mathematics are called bifurcation points. So one approach one can use in this connecting of math and science to the real world is have students read a book that has some real world interest. And I've been very interested in the writing of Gerard Diamond. He wrote the very popular Guns, Germs, and Steel, but he also wrote another book called Collapse: How Societies Choose to Fail or Succeed. This book had quite an impact on me, the idea that in the past, societies that had been very successful at some point fail and collapse, and the idea that our present societies in the world, and even our global world society as we face climate change and environmental degradation, could potentially fail. It's a very thought-provoking and sobering argument. And originally I had the students read the entire book, and for each chapter in the book, the assignment was to write a short half page to a page write-up explaining how do you see the topics from our course relate to the different chapters in the book on collapse. And this went fairly well. The students posted their writings and we discussed them a bit in class. But the end of course feedback was that they felt that this was too extensive an assignment to add on to their differential equations course, having these reading assignments every week. So in later years I modified the assignment and I just had them read a few select chapters from the book. And one of the chapters they read was dealing with Rwanda and the genocide in Rwanda in the mid-1990s. The connection to our course is that the author discusses the fact that Rwanda is one of the most heavily populated nations in the world, and that a contributing factor in his estimation to the genocide was this overpopulation of the country. And population growth is a very standard topic in our calculus classes and also in lower level courses. You have a differential equation and the solution to it involves an exponential. So the assignment we made up, one of my students, Wen Gao, who graduated in 2007, worked on this, and it grew out of a conference we both attended at Lafayette College in 2006 on math and social justice, was taking material from the chapter on Rwanda and turning it into a population growth problem. Here I'll give you a minute to look at the assignment and the data. So here we ask standard things: what's the growth rate? What's the doubling time with this growth rate? Given the data table, calculate the growth rate, figure out the exponential solution. And then the key connection is, how does your predicted population match the actual population for 1995? And what the students find is their exponential model overshoots the population in 1995. And we ask why. And in this case, it was because that was the time of the genocide when the population was decreased, and also perhaps that people fled Rwanda for neighboring countries, and so the actual Rwandan population went down. Then we discuss the idea that we're making a model, and models have limitations. So what are problems with the exponential model? What's it good for? What does it do a good job of predicting, but what are some of its failures? So if you like, you can pause the webinar and discuss with your group this issue of modeling using an exponential function. Well, one weakness of the exponential model is that it predicts the population will grow to infinity. And we know you can't, in real life, have a population becoming infinite. A strength of the model is over a short time period, it does often predict the population growth fairly accurately, but only over a finite period. So that leads to our next topic in the differential equations course, the notion of a carrying capacity, that the environment can only hold a certain finite population, and this leads to the logistic model of population growth, which is written below. And the notion of carrying capacity is a key idea in issues of sustainability, and in many other fields besides math, students will learn about this. We don't actually know in a given situation what the actual carrying capacity might be, but the concept of a carrying capacity is very useful. And then we can study the solutions of the differential equations using what are called slope fields, getting this visual representation that if you begin with a large population, it will decrease towards an equilibrium solution. If you begin with a smaller population, it will increase to the equilibrium. Zero is also an equilibrium. If you start with no zero population, it will remain zero. And at least mathematically, if you begin with a negative population, it will go to minus infinity. So here we see if the population starts above the carrying capacity, it will decrease and approach that capacity. And if you have a smaller population, then the population can grow, but it limits towards that carrying capacity. We call the carrying capacity an equilibrium solution. If we begin there, we stay there. And also zero population is an equilibrium. And we can, in shorthand notation, draw this one-dimensional diagram called the phase line that shows these equilibrium solutions. Above, the solution goes down. Below it, it goes above. And if you're negative, you also go down. So we call this equilibrium an attracting equilibrium, and the zero equilibrium is called a repelling equilibrium. So this helps us analyze the situation of having a carrying capacity. This then leads into the next topic, which is having growth with a logistic equation, but then we have harvesting. And mathematically, in our differential equation, that is represented by this term minus h, that each year h members of the population get harvested. And then the question is, well, what kind of populations are we talking about? And one very important one is fish populations. And by harvesting, we mean the fish that we catch. Another example, which maybe is a little less intuitive, is forestry and logging. And the population is the population of trees. And the harvesting is how many trees do we cut down each year. So here we immediately see a nice connection of this important concept of the population growth with harvesting to real-world situations. This harvesting, we can think of examining the differential equation with different levels of harvesting. And what we'll find is that as the harvesting level changes, there are certain critical values of the harvesting level called tipping points, or mathematically we call them bifurcation values. And as we change the harvesting level past these critical values, the behavior of the population changes dramatically. This notion of a tipping point, or mathematically we call it a bifurcation, is a very important concept that has really crucial applications in our 21st century world. So I make a special effort to create some experiences for the students that will help them engage with this concept, first in a more intuitive real-world setting before we get into the mathematics. So here is this idea of trying to connect their previous knowledge about the world to a complicated mathematical concept. As we'll see, mathematically, a bifurcation point is built on 3 or 4 ideas, one on top of another. So it's a very complicated mathematical object, and I want them to come into the mathematics with some real-world understanding of it that's going to help them deal with the mathematics. So here I go back to the book Collapse, and I have them read the chapter on Easter Island. And we learn that on Easter Island, where you have the famous statues, they had a very thriving civilization, which for some reason at some point died off. And so part of the assignment is to read about Easter Island and then write up what factors contributed to the collapse of the society. And one thing they find out is the idea that the forests on Easter Island got harvested to perhaps help move these large statues, that the trees were used maybe to roll the statues. In any case, eventually all the trees disappeared, and that caused problems for the society, which had been depending on the wood up until that point. And some of the students think, well, how silly of this society. How could they have not realized, as they were using up the wood and cutting down the forest, that this was going to cause a problem for their society? Next, we have a very special event in the course where we play a fish simulation game. And at the beginning of the term, I announced to the class that we're going to do this, and this is going to take 3 hours, and we're going to have a special evening meeting where the class meets to do this. And we play a game called Fish Banks, which is a study of renewable resources developed by Dennis Meadows, who is well known for the book Limits to Growth, and collaborators along with his partner Dana Meadows. And in this game, the students are in teams, and they are running a fishing company where they have their own fishing boats, and the goal in the game is for them to maximize their profit. And they take turns. Each turn corresponds to a different year. They can buy more fishing boats. They fish, they catch fish, they get income from the fishing. And what happens as the game goes on, and it's shown in these graphs, over time they crash the fish population. First they go to the deep sea where they could catch more fish. They overfish that and the deep sea fish go to zero. Then they switch to the inshore fishing. That fishing stock lasts a little longer, and then they crash that fish. And so once they've crashed the fish, their initial profits that they made by all their fishing stops, and they no longer are making a profit, and they are losing money because they still have to pay for the upkeep of their ship. They've fallen prey to the tragedy of the commons, that individually it's in their best interest to catch as many fish as they can, but if all the different teams follow that strategy, the fish population decreases, the population will go to zero, and then they can no longer make any profit from fishing. The phenomena they're dealing with is also called overshoot, that the data they get of how many fish they catch each year, if they pay attention to that data and act logically based on that data, they will actually keep fishing beyond the point where the fish have started to decrease. And by the time they notice that there's a problem, it's actually too late to adjust course and decrease your fishing level. You've already crashed the population. And this happens in the real world. We saw that with the economic collapse in 2008, with the real estate bubble. The car industry had a crash from selling too many high-priced gas-guzzling cars, that by the time you realize there's a problem, it's too late. So the students have had this profound experience of themselves overfishing, and they realize that they, just like the Easter Island people, can easily fall prey in the moment to using more resources than will last in the long term. So here I've set the stage for now the mathematics of this overpopulation and crashing of population by this real-world experience. So the mathematics involved is something called a bifurcation diagram. It's made up of a bunch of these phase lines, these vertical lines that we looked at earlier, and for each different fishing level, you have one of these vertical lines. I have the students in teams do a jigsaw exercise where they each have a couple of H values, and they draw their phase lines for those H values, and then the other teams put in their phase lines, and together we produce this whole diagram, and we kind of connect the dots of the equilibrium to get what we call the bifurcation diagram. And the key point is that there's a critical level, which we can call the tipping point or the bifurcation value, beyond which the fish population crashes to zero, and below which you have an equilibrium value, and the fish population could stay at that steady state value forever, and one could fish profitably at that level without ever crashing the population. So here we can see how mathematics can help us understand a real world situation, and going forward one could, for example, try to help the fishing industry regulate itself by using this notion of tipping points or bifurcations, so it doesn't crash the population and put all the fishermen and fisherwomen out of business. So here we see this issue of the critical fishing level. One takeaway is that if you're near a tipping point, what would seem to be a small change in the system, increasing the fishing level by just a small amount, can actually have a drastic impact on the outcome. You can go from a steady state level to crashing the population. So those were some examples I had come up with in my differential equations course. Here is one of my heroes in the work of math education, Tom Paff from Ithaca College. And he has created quite a number of modules relating sustainability to math, to calculus, and also statistics that one can just plug in to math courses. So we'll talk a bit about this idea of these ready-made modules. I'll share one that I've created based on Tom's model at Bryn Mawr College, where I teach. Here we see off in the distance a small solar array that we have on our campus. How many of you have solar arrays on your campuses? You might want to take a pause now with your groups and talk a little bit about what do you know about solar power and solar cells, photovoltaic solar energy. So let's take a pause and you can have a little discussion in your group. Here, let me backtrack a bit to our educational theory. One reason I have you doing this discussion about solar energy is because I want you to bring out of long-term memory what you know about the issue of solar energy. And then once it's out of long-term memory, it's ready to be accessed so we can connect this pre-existing knowledge you have to the new knowledge we're about to do on the math of solar energy. And also, as you discuss, I can go around and listen to you and find out what misconceptions you might have about solar energy that I might want to try to address during our lesson. So we're going to see a lesson on solar energy, but before we do, we're going to take a field trip and we're going to walk across campus to the solar panels and take a look at them and talk about solar energy. So I did this as an optional outside of class event, and about a third of my class showed up and we walked over to visit these solar panels on our campus. Well, these solar panels are connected to a website where we record the power that these solar panels generate. And here we see several days, 1, 2, 3, 4, 5, 6, 7 days way back in January 2014. And here we have beautiful graphs. As a math teacher, I always love having graphs and data. And a question for you and your group is, why do these graphs look different on different days and at different points in the day? So discuss that for a moment. So as your group probably decided, the weather was different on those days. On a cloudy day, you'd have very little solar power being generated. On a sunny day, much more. And as the day went on, you might have moments of cloudiness and then others where the sun is shining brightly. So this is the power produced at different times of the day in units of watts. If you think of a light bulb, a 100-watt light bulb, which is kind of a former standard being kind of changed now as we have new compact fluorescent or LED bulbs. But the rating of 100 watts means that each instant the bulb is using 100 watts. More technically, a watt is a joule per second. So power is a rate of energy use. So during the day, your solar panels are producing this amount of power. And if you add up the total energy produced in the whole day, you get another set of graphs. So again, as a mathematician, this is wonderful. Here we have graphs. So this gets to my point about certain aspects of sustainability. You cannot study them without using mathematics. If you're looking at energy use, energy production, you're generating graphs, and graphs and data are mathematics to be analyzed. So the problem I want to focus on is, given one of these power graphs, here we have one from January 17th, how much energy is produced over the course of the given day? So more generally, what's the relation between the power graph and the energy being produced? So here we have a handout that you can work on with your group where you explore for yourselves the units of power, which is the watt, the unit of energy. You can use the electric bill that comes in the packet to see the units of energy. And then what is the connection between energy and power? So pause the video now and work through some of this sample lesson. So let's come back together again. If you looked at the bill, you saw that the unit of energy is kWh, which stands for kilowatt hours. So we talked of the 100-watt light bulb. If we have 10 of those bulbs going together, that uses 1,000 watts. That's 1 kilowatt. And then if we had those 10 light bulbs running for 3 hours, the energy we would use would be 1 kilowatt times 3 hours, so that's 3 kilowatt hours. We get this new unit of energy, which is the kilowatt times the hour, 3 kilowatt hours. And in your worksheet, you notice that you can represent the area under this little problem of the fixed power times the time as the area in a rectangle. Or in a more complicated example, it's the area in several different rectangles. So here we see the very important idea that a physical concept can be the area under a graph. And if we go back now to our more complicated power graph, the extension from our simple examples of power and energy is that the energy produced over the course of the day is the area under this graph. And if you've had calculus, you know that the area under a graph is one of the key concepts of calculus. It's the notion of the integral. And so here we have a real world problem of an important type, solar energy, that leads us to need to calculate an integral. Partly I was motivated in making this problem by overhearing a few students in the gym at my college. And they were talking of their math lesson that day where the professor spent a lot of time talking about a really complicated thing called Riemann sums, which is adding up little boxes, and you take more and more boxes, and you take a limit of the number of boxes going to infinity, and you find out what the limit of the area is produced by these boxes. And the students said, and this was really annoying because at the end of the lesson, the professor said, but all this stuff with the boxes is equivalent to taking the antiderivative. Well, why didn't he say so at the beginning? Why did we have to spend all that time doing this complicated Riemann sum? Why didn't we just do the antiderivative from the get-go? Well, I would hope in this lesson on power and energy, we do not have a formula for this curve. All we have is a set of data points which we can keep in a spreadsheet, for example, and the power is given by that data, not by a formula. So we don't know how to take an antiderivative because we don't have a function or a formula. So we really have to add up boxes to find the area under the curve. We think that on a very short time interval, the power is about constant. So we can approximate this curve by a bunch of short horizontal lines and then find the area under all those lines. So not only can sustainability illustrate an important idea of calculus, the integral, but it can actually force students to think about it in a deeper way, where they confront the fact that integrals have to deal with real-world data that are not given by formula, and so they need to really understand the notion of a Riemann sum, which leads into the idea of numerical integration with, for example, the Euler method or the trapezoid method or the Runge-Kutta method. Numerical integration with Riemann sums using boxes, using trapezoids, the more complicated Simpson's method. So this one example can link into a lot of material in the course about mathematics of calculus. And then I try to end this unit with a big question. Do you think it's worthwhile for your college to get solar panels? Would it be worthwhile for your home or your community to have solar panels? So making a connection problem, linking the mathematics back to a real-world example. And one could, if one wanted to, have the students research that. I'll talk a little bit later about service learning projects where they do these things more extensively. But one could just make a simple question and have them write a paragraph. One could also ask them, what kinds of questions would you ask and what information would you need to gather to be able to answer this question of whether it's worthwhile to get solar panels? And that lays a good groundwork for the whole issue of mathematical modeling and how do you use math to answer a real-world problem. Okay. Beyond using these sustainability units in differential equations and calculus, I've also used them in courses on math modeling. I've developed a course called Math Modeling and Sustainability, and then a version of that course is our senior seminar for our advanced students. And here are some of the resources I use in the course. A beautiful book called Math Modeling in the Environment by Charles Hadlock, some of the sustainability units by Tom Paff. In the Hadlock book, there's a nice chapter on groundwater flow that leads into the Laplace equation. We look at solar energy, we look at wind energy, we look at energy in houses and insulation and how that can conserve energy. Also the leakage around windows and doors, how does that affect energy use? And in these courses, I have the students do a service learning project in partnership with the community. And as I've gotten more involved in this idea of math modeling and sustainability, it's led me in new directions. I became the chairman of our college's sustainability committee. I've now become the director of our environmental studies program. So a little word of warning as you begin linking your math or science teaching to issues of civic engagement, it could lead you in exciting, new, but very different directions. So Bryn Mawr has joined the President's Climate Commitment program, and now we're also in the ASHE program, where we're trying to reduce our carbon footprint. So that gives me the opportunity of linking the student service learning projects to actual issues that the campus is facing. Another great resource for the course is a book, Sustainable Energy Without the Hot Air by David McKay. It's available free online, and it uses, in many cases, just high school algebra, but in very clever ways to model the issue of sustainable energy and is it possible actually to scale up from small levels of renewable energy, wind and solar, to large-scale renewable energy that could power our entire nation. So let me talk a little bit about the service learning projects that I have the students do in conjunction with the classroom work. And as I look back over the projects the students have done, they fall into a couple classes. One is the issue of waste, another is energy. And in these projects, we work with a community partner, but we've broadened the notion of who a community partner is to include our own institution as being part of the community. And so quite a few of these projects, the community partner was staff members in the facilities department. These people are very knowledgeable about issues related to sustainability in the environment, and they're very eager to be involved in the educational enterprise of the institution. Many of them, one of the benefits and joys of working at a college institution is getting the chance to interact with students around projects of this nature and playing a role in the educational enterprise. And so many of these partners have been the staff who supervise and guide the students on these projects. The first project I mentioned is the trays in the dining hall, and it was the question of whether we should stop using trays. Would that cut down on food waste, and would that save money in terms of washing costs? And what the students found out is it would save food waste. They did a weighing when they had trays, and then one day when there were not trays. And then they also estimated it costs about 5 cents to wash a tray when you take into account the cost of the hot water, the cleaning supplies needed, and also the time of the workers. And 5 cents does not sound like much, but they estimated when you count how many trays get used through the course of a year, that adds up to $38,000. And they presented their report to the dining directors, and the end result was we no longer have trays in the dining hall, that you carry your plate and you might have to go back multiple times if you want to have big helpings. Growing out of that issue, students began looking at composting. Could the college compost its food? Initially, the composting company they used in a pilot project came from Wilmington, Delaware, which was about 30 miles away, and it made that 30-mile round trip 3 times a week. And so it wasn't clear that there was actually an environmental benefit to having composting if we did it with this particular company. So the students analyzed these benefits, they analyzed the cost, they found a new composting company that was much more local, and then with this new company in their analysis, there was a definite benefit to the composting, and the money we saved by reducing trash output from the dining hall would pretty much pay for the composting. So that was, again, they gave a report to the college dining services, and it led to this now widespread composting project. Growing out of the composting, this idea that there was less trash being generated, that got the facilities people thinking about, are we really using the trash bins, these big dumpsters around campus, to the full extent? Or are these trash bins only partially full? Since we pay by the pickup and by the size of the trash dumpster, if the dumpsters are not being fully utilized, maybe we could have less pickups per week, or maybe we could have smaller dumpsters, and that would save the college money. So the trays led to the examination of composting, led to a trash audit where students worked with the facilities department to measure every day, several times a day, how full the trash dumpsters were. The facilities people painted lines on the dumpsters, quarter full, half full, 3/4 full, and the students recorded how full the dumpsters were and presented their findings and a recommendation that in some cases they could reduce the size of the dumpsters and we wouldn't have any problem of overflow. That would be a very bad thing if the trash overflowed onto the ground, and so we wanted to make sure that would not happen. As a result of that project, the facilities people, when they signed the new trash contract, reduced the size of some of the dumpsters and ended up saving the college $1,000 a month. So through these projects, the students have an excellent experience of facing a real-world problem, and in many cases, they've had a real impact on our institution. I'll just briefly mention some of the other projects they've done. They worked with the local school district to analyze whether the school district should handle its trash system and recycling system with an outside company, which is how they presently did it, or would they actually save money by handling it in-house. On the energy front, students looked at whether we would save energy if we put the buildings into conservation mode. We had not really realized it until the students asked the question, can we save energy in the way we run our buildings? But they found immediately that some of the buildings were heated and cooled to kind of a comfortable temperature 24 hours a day, 7 days a week. And partly this was explained that one of the buildings was being kept in good working condition all night long in case students wanted to have meetings in this building. This was one of the buildings that students could use for midnight meetings. Well, what we immediately realized as we talked about it was, as far as we know, students have never had a meeting in that building in the middle of the night. So this idea of keeping it well heated or cooled in hot weather was just an absolute waste of energy and money. And that led to a whole review of the college policy where we realized that actually all the buildings were being heated or cooled 24 hours a day. So even before the students had done any advanced math, simply by asking these questions they came up with, they got people thinking in new ways that led down the road to changes. So over a 3-year process, the facility staff and the sustainability committee met with people in every building, discussed issues of conservation and sustainability with them, presented the findings of how much energy we could save if we reduced the temperature during the night and made sure that all the lights were turned off, and asked each building to come up with their own hours in which we would set back the temperature, what we call conservation mode. And so that big impact on the campus grew out of the student work. They looked at savings for putting LED bulbs into the lights. They looked at how much savings we could get if we put on-off switches on some of the chemistry hoods. Right now, the research hoods don't have any off switches, and so they're in use all the time, even if there are no experiments being done. And that turned out to be a significant energy savings. They worked with a local township where they were creating a new recreation center, and they wondered about putting alternative energy features in the center. They worked with a retirement community that wanted to be more sustainable, and the students analyzed energy use, particularly around light bulbs for them. So there were a wide range of projects the students did, and often the end result of one project would lay the groundwork for the next. I'll mention the one about the recreation department in a little more depth. Here's a architect's rendering of this beautiful new recreation center, which has now been built. And the students were asked by the township commissioners to look into whether there should be solar energy or wind energy in the building, and also geothermal energy, which is the idea of using the heat from the ground to help heat the building in cold weather, and using this 55-degree constant temperature from the earth to also cool the building in hot weather. So their final exam, if you want, was giving a presentation at the Board of Township Commissioners meeting at the end of their semester, talking about their findings, recommending that solar energy was a possibility, but that the real savings would come from putting in a geothermal system. As well as saving money, it would also reduce the carbon footprint. And the township commissioners eventually voted unanimously to put in the geothermal system, even though it would cost an extra $500,000, but it would save $50,000 a year. So the students had convinced them that it would pay off and it would reduce the carbon footprint of the township. Growing out of that project, the following summer, the township was going to apply to the state for a green energy grant of $300,000 to help pay for the geothermal system. And two students who worked with me in the summer took the data that the first students had done and helped the township write the grant, and also simply putting all that data into an online computer system, which is how the grant was being run. The township staff was not so facile in dealing with this computerized system, and the college students were much more knowledgeable and were very helpful in entering all this data. And at the end of the summer, the township got the $300,000 grant, and the commissioners created an official proclamation of thanks, which they presented at a township board meeting to thank the students for their efforts to help win this $300,000 grant and help the township be more energy conscious. At the end of the semester, I asked the students for their reactions about these projects, and so here I'll give you a minute to read what they said. So if you want to take a pause for a moment with your group and discuss these student reactions and what you might anticipate being student reactions on your campus, or if you've done student community-based learning, service learning, what student reactions have you gotten? Another interesting finding was the students' reaction to the math involved. They said the math involved in most of these applications was pretty basic. They said that there were more numbers than mathematics involved in our projects, which for non-mathematics people might seem a little funny, because one would think, well, mathematics is numbers. But at a higher level of mathematics, it's theory and maybe formulas, and actually not so much numbers. So what we found in these praxis projects was we were focusing more on math modeling and quantitative reasoning, which is a big issue in the math world, teaching students how to make sense of the world using math and quantitative notions, even if it isn't very sophisticated mathematics. But to use even basic mathematics in a real-world problem is a very challenging skill, which is different than doing abstract mathematics, and it's a skill we want our students to have. So these real-world problems, the math modeling involved, even though it didn't use sophisticated mathematics, was very challenging because it let students engage with this problem of mathematical modeling of the real world. And these service learning projects I've been talking about, I've written an article for the Premis Journal. They had a special issue on mathematics and service learning where my article appears. Here are pictures of two of the seminar classes that did the service learning projects. And there's a lot of focus now in the education world on assessment. So I did the survey of the students. I didn't do a more numerical type of assessment. But the students, in a sense, did their own assessment. They posted this picture on Facebook, and they made a few comments. They said, "Best math senior conference ever. A great semester with you. This has been my favorite math class in all 4 years." So they're in their own voices. They're showing that this was an exciting experience. They enjoyed using their math in a real-world setting, and they felt empowered that they could make a difference in their community using their knowledge. And that's really one of my goals as an educator, to have students feel empowered and for them to realize that they have knowledge and skills that can make a difference in the world. Another takeaway I had from that is that in doing these service learning projects, a wide range of skills is necessary. In my typical math class, often the main skill is mathematical strength. And students who are weaker in mathematics don't get a chance to shine. But in these service learning projects, students who are good at leading a group, at setting deadlines, at dividing up tasks, at reaching out to the community partner, at gathering information, all these skills are valued and important, and students with this wide range of skills all get a chance to shine, be recognized by their teammates as making valuable contributions, and seeing their efforts pay off. And as an educator, it lets me feel more of a sense of connection with these students and have a more positive attitude when I can see all the students succeeding, rather than in a traditional class where only a small minority of the students, the one with the most gifted math abilities, get to shine and succeed. So it's made my job as an educator more pleasant because I get to see more of my students succeed. Bunch of mechanics that go into doing a service learning project. One is, of course, finding projects. You might work with your local Office of Civic Engagement or Service Learning if you have one. Over time, I've built up a network of community contacts. But let me stress again the value in using staff members from the college as partners. They're very knowledgeable, and my experience was they were happy, eager, and enjoyed interacting with the students. One of the staff members, the director of our dining services who oversaw the initial tray project that I talked about, said that in her 20 years at the college, this was the first time that a faculty member had invited her to be part of the educational enterprise. And she really appreciated it, and she enjoyed it, and she did a wonderful job in sharing her knowledge with the students and being part of the change that happened as a result. It's very important to give the students a voice in selecting their projects. My approach is usually to develop 3 or 4 possible projects ahead of time, bring the community partner in at the beginning of the term to present the project, have them stress how important it is, how the student work will be used by the partner in making a decision, and what the decision is that the partner is trying to decide on. And then the students get to select first, second choices out of that range. And usually in this way, they end up working on a project that they're excited about. Over time, I learned it's important to manage expectations, that often the projects do not go smoothly. Unexpected things happen. Sometimes the projects have to move in a new direction. They've reached a dead end. The timeliness of the project might be affected. Sometimes the partner has had things happen on their end that made the initial plan not work out, and the students have to do a different aspect of the project. And initially, students will get very upset. They're used to it, particularly in a math class, having structure, having things work out, being able to follow a plan step by step. And so now I talk from the get-go that these bumps in the road are going to happen, and that this is actually one of the prime features of a service learning project, And it's a great opportunity for them to engage in this real world problem of being adaptable and dealing with difficulties along the way. So what in the first year was a lemon and got the students very upset, I now try to turn into lemonade by having students look forward to their unexpected road bumps, and we celebrate it when it comes up and they talk about it in class. I've also recently started linking these projects to learning goals. We have a new center at the college which combines career and professional development and civic engagement. We call it the Lilac Center, Leadership, Innovation, and Liberal Arts. And there they have come up with a bunch of learning goals that we would like to think our students take away from the entirety of their college experience. That they're interested in exploration, self-discovery, conceptual thinking, reflective practice, connections between different areas of their lives and the world, culturally competent, social responsibility, communication. And so the last time I taught the course, I had one of the service learning directors come into the class and talk about these college competencies, and then have the students decide for themselves which areas they felt they were strong in and which areas they would like to improve and try to work on through the service learning project. This linking of my class and the experience in this one class to these larger college goals, I think sent the message that what I'm doing is not like a weird, unusual thing where I'm making them do this extra work that other students don't have to get. Rather, I'm giving them this valuable opportunity to develop these important skills that the whole college thinks is important. So this linking what happens in my class to these larger college goals, I think, is important. Again, partly to get student buy-in, where they realize that this is an important, valuable experience. We keep track of student progress. They post updates. Actually, if I do it again, from the get-go, I would set up a journal where the students each week would write updates in a journal and also report meetings they have with the community partner. As well as spending time in class on a regular basis where the students get to report to one another how their projects are going, and we also spend time where they just get to work on their projects, because it can be hard for them to meet outside of class. And I want to stress that I value these projects, and so I'm going to devote some of the class time to them. Finally, they give a written report and they give an oral presentation both to the class and to the community partner. And we have a bit of a celebration at that event, celebrating the success of the whole semester. And we invite members of the college community, members of the college sustainability committee to come hear these reports. This brings me to another topic. Growing out of this work I've done on math and sustainability, which is a nice place for some resources that you might use connecting math to sustainability, which is the Mathematics Awareness website. Every year, the main math societies of the United States work together to sponsor Math Awareness Month in April. And each year there's a different theme. And in 2013, the theme was the mathematics of sustainability. And I was invited to be the chair of the advisory committee, which I was very pleased to take on because I think this is such an important topic. So as part of Math Awareness Month, we made this poster. And if you read it, you see our tagline is balancing needs and seeking solutions for a complex changing world, which gets back to the basic definition of sustainability, where we have to balance the needs of the environment, economic needs, and social needs to produce our sustainable society. So here you have the address of the Math Awareness Month website, where there are a bunch of resources. One is a bunch of short essays, 2 to 3 pages, talking about how mathematics gets used in different areas of sustainability. We have essays by architects, by urban planners. We have essays by academics talking about more research-oriented aspects of sustainability. We have one from the Philadelphia Phillies baseball team. I live in Philadelphia. I was very excited to get an essay from them, talking about their work as a green business organization and how they use mathematics to be a green business organization. So one could assign to the students, choose one of these essays, read it, and then write a one-page summary of what it's about and what ideas it's given you about how math gets used in sustainability. Students could post these answers again on the class Blackboard site and read each other's. Again, letting them see how math connects to the real world. There's also a number of educational units, and the one we did earlier together about the solar panels is one of the ones up there under the Sustainability Counts links. And then there's finally a more general link called Other Resources. So among the teaching units, there's one on CO2 levels that Tom Paff made, and there's one on Arctic sea ice levels and trying to predict when the Arctic will be ice-free. One of the essays that I found very thought-provoking was by David Schiller, who's a light bulb designer and has designed some of the new light bulbs. And I encourage you to read his essay. As I said, it's thought-provoking. And he asked the question, why do we have a global environmental crisis? How did humanity get to this point? And thinking about it, he became kind of philosophical. And he thought about Descartes, who talked about, I think, therefore I am, and the mind-body separation that we have in Western philosophy, that our thinking selves is kind of separate from our emotional selves, and that we're trying to emulate more the intellectual, mental side and not pay attention to the body part of our being. And that using thinking we can figure out things about the world, we can find solutions to problems, we can kind of dominate nature by using our minds. And this kind of laid the groundwork for the Industrial Revolution, the Age of Reason, that using thinking we can make sense of the world. But it also led to the idea that we can dominate the environment, we can create machines to change the environment in different ways. And this worldview, which comes about in subtle ways from these mathematical ideas, David argues that this worldview of the mind being separate from the body and then the mind being separate from nature is a contributor to our environmental problems, that we've gotten away from the fact that as human beings, we are in the world, we have to live in harmony with the world, that we have an affinity for the world. And these same ideas can even be thought about with issues of racism in the world and inequality. Somehow our human selves have been hurt so that we're able to mistreat other human beings in the same way that we mistreat nature, that we view these others as separate from ourselves. So it's a very thought-provoking essay, and it makes us think about how, on the one hand, mathematics can offer, and science can offer, help in dealing with environmental problems and social issues, but there's also a way where we've contributed to these problems, and if we're going to have a sustainable world, we need to be more in harmony and use our powerful thinking to solve the problems of the world, not necessarily make the problem. So this argument that we separate mind and body, and that Western philosophy has encouraged us to think more of the mind rather than the body, this sensor program of linking our teaching to issues of civic engagement, for me personally, it's been an opportunity for me to reconnect the different parts of myself. I love mathematics, I love the abstract nature, the reasoning, the beauty of it, but I also care about these issues of the world, of social justice, of the environment. And in the past, I kind of had to check those issues at the door when I went on to my math teaching. But now through the sensor approach, I'm able to incorporate those issues I care about and that my students care about into my math teaching. So it feels like I'm becoming more a whole human being rather than a human being separated into different pieces that lead separate existences. So I think that's an exciting opportunity that we have through this type of sensor work of reintegrating the different parts of ourselves. Worse. So I'm still trying to come up with a version of, a new version of Descartes' statement. Descartes said, "I think, therefore I am." I invite you to think about what would be a different version that would resonate more with this idea that we are human because we are connected to each other and to the world. I'll toss out as a suggestion, I am connected to others and to the environment, therefore I am. A final piece growing out of this work, and I mentioned how once you begin moving down in the direction of linking your math and science teaching to issues of civic engagement, in my case, the environment, one thing leads to another. Kind of out of the blue, I got contacted by the TED Ed people. The TED people have these talks by experts. TED Ed is a slightly different thing where you make short animated videos dealing with some educational issue. And they asked me to propose a topic. And based on my work in these courses on differential equations and the importance of the notion of tipping points, I came up with the idea of examining climate change and the role that tipping points or bifurcations play in that issue. So I wrote a script. That was my main job, an 800-word script that got turned into a 4-minute animated video by an animation company in England. And now I'll give you a chance to look at this video. The link is right here with the address. Also, if you Google TED Ed and Dane, you'll have it pop up. So there we see how this notion of a tipping point, that as we change the conditions of a system, even a little bit, the system itself can have very dramatic changes. And for climate, it's the idea that as we change the level of CO2 in the atmosphere, the way the climate behaves can change from what has been a fairly benign, pleasant climate for the last 10,000 years into a much less pleasant climate with more extreme weather events, higher temperature, more droughts. And so mathematics has a role to play here in the real world of educating people about the concept of a tipping point and that a small change in a system can have dramatic impacts so that people can better understand this really important issue of climate change. Here I'll just show a slide or two of another aspect of my work with math and sustainability, which is working with K-12 teachers in the Philadelphia region, both math and science, in a summer institute, helping them think about how they can connect issues of sustainability to their own math and science teaching. And so as you do this important work at the college level of developing new courses that link math and science teaching to other disciplines and to issues of civic importance, I'd encourage you also to reach out to your K-12 colleagues and work with them to support their efforts in a similar direction. And also, as you work with new prospective teachers, get them engaged in thinking about how they would incorporate service learning and issues of civic engagement in their teaching. So here the teachers are talking about lessons that they would do when they go back to their classroom. And here you see them doing hands-on work. For example, examining the energy use of different types of light bulbs and examining the question, is it worth it to change light bulbs? And we took a field trip to the Philadelphia Waterworks Center to learn about issues of water use, which has lots of nice mathematics. For example, if 1 inch of rain were to fall on your schoolyard, how many gallons of rain runoff would that lead to? And the unit we did on the solar energy, let me say that I was inspired to create that based on the example of a lesson that one of the teachers in the Summer Institute created. She was looking at when are we going to run out of oil, the notion of peak oil, and looking at the area under a curve and estimating that area. So there's fruitful ground for collaboration with our K-12 colleagues in this area of linking math and science education to the real world. Let me end with this final slide showing my colleagues in the Bryn Mawr Math Department. So our logo is do the math, feel the power. The idea that in our modern 21st century world that is so technological and computer driven, having a strong math background is essential to being able to take part in many areas of our society. And so having a strong math preparation in school is really a civil rights issue of the 21st century. That if students don't have a strong math and science background, they're being shut off from so many areas of society, so many potential opportunities and careers. And here we see a flag that the department hangs to celebrate our being awarded in 2012 the American Mathematical Society's Exemplary Program Award for our success in having so many women math majors in our program. Roughly 10 to 12% of the entire student body majors in math at Bryn Mawr, and the national average is less than 1%. So thank you very much. I hope this webinar has been helpful in stimulating your thinking about a wide range of ways in which we can use issues of civic engagement in math and science classes, some of which are very easy to do. We saw the examples of just supplementing a homework problem by asking students to connect it to the real world. Some may be moderate, where you have a lesson using an issue of civic engagement that you plug into your standard material, and some more elaborate, the service learning that maybe will take a while before you're ready to do. Some takeaways are the idea of using real data, which again in a math class often we haven't done in the past. Maybe there's some made-up data in the book with simple numbers, but using data about the real world, data from your own institution, like the data about the solar panels. There's data on the CO2 levels that's mentioned in the CO2 lesson. I think that makes the math more exciting for students, where they see these real world connections and that math gets used in the world. And the fact that the numbers in real world data are not neat and tidy deepens our students' understanding, because they have to figure out how to use math in these messy situations. So thank you again, and let me end with my Bryn Mawr logo. Do the math, feel the power.